This is an audio recording of ESPRESSO 43, which was published in August 2022 and written by Fran Watson, Lucy Rycroft-Smith and Tabitha Gould. The ESPRESSO is copyrighted by Cambridge Mathematics and was published by Cambridge Mathematics in partnership with Cambridge University Press and Assessment, the University of Cambridge Faculty of Mathematics and the University of Cambridge Faculty of Education. This audio version was recorded by Mike Dowds, Lynn Fortin, Luc Moreau, Moussa Simbi and Fran Watson in July 2024 and is copyrighted by Cambridge University Press and Assessment.
ESPRESSOs are two-page filtered research documents from Cambridge Mathematics. Each one focuses on selecting and summarising research on a given area of mathematics education called a talking point. They are published as free PDF documents on the Cambridge Mathematics website www.cambridgemaths.org.
This CoffeePod is 23 minutes and 41 seconds long in total.
It comprises the following sections: a talking point, quotes, a summary, the main text of the ESPRESSO, the infographic, and an optional reference section which is also available as a separate document linked in the video notes. You will hear the following sound to indicate a reference, followed by the reference number to help you identify it. The chapter timings for the different sections and a link to the original published ESPRESSO can also be found in the video notes. You can give us feedback or ask questions in the comments section under this video. We'd love to hear from you.
Talking point.
What does research suggest about the teaching around factors, multiples and prime numbers?
Here are two quotes from the research that you might find interesting to think about.
That is part of what makes primes so interesting. Not only is the number line studied with primes all the way up to infinity, but that the whole number line can be produced using nothing but primes.
This was written in 2020 by Graham Templeton in an article on Mashable.com called "Why Should We Care About Prime Numbers?" Reference 1.
The operation of addition or subtraction is the same as extending or cutting off lines. The product of two numbers a and b is the same as the geometric construction of a rectangle having adjacent sides a and b.
This was written in 2014 by Joseph Mazer in a book called Enlightening Symbols, A Short History of Mathematical Notation and Its Hidden Powers. The quotation can be found on page 143 of the book. Reference 2. In summary, we found 7 main implications for teachers in the research. We have numbered them here for ease of listening, but they are not intended to be hierarchical. That is, no one implication is more important than any of the others. The 7 implications are:
1. Decomposing numbers to investigate their multiplicative structure can support a flexible approach to problem solving and should come before the introduction of rules or procedures. 2. Activities in which students sort objects into regular arrays of width 2 and explore which numbers can be split into 2 equal groups and also into equal groups of 2 all support conceptual understanding that even numbers are divisible by 2. 3. Students need to link doubling to multiplying in order to appreciate when it will always result in an even number. 4. Visualising building numbers by scaling or growing rather than by repeated addition helps support multiplicative reasoning and generalising. 5. Working with characteristics of primes can help avoid misconceptions about their size and prevalence as factors of other numbers. 6. Practicing seeing prime factors both individually and in combinations can help support flexible reasoning about the divisibility of the entire number. 7. Making links between different methods of finding the lowest common multiple of two numbers can support conceptual understanding. Venn diagrams are suggested as useful ways to visualise common prime factors of two numbers.
Here is more detail about the research which fed into the summary implications, organised into 5 paragraphs, which each have a set of implications for teachers at the end. Paragraph 1.
Developing an awareness of the underlying multiplicative structure of whole numbers can support a flexible approach to problem solving.
Reference 3.
Creating and considering equivalent representations of the same number, which is discussed in the infographic section, and the related concepts of factors, multiples and divisors can reveal general properties about families of numbers such as odd, even, composite and prime.
Reference 4.
Research is scarce on school students' experience of using primes to build numbers, but some exists on teachers' learning of and teaching around these concepts.
References 5, 6 and 7. There are 2 implications of paragraph 1. First implication.
Decomposing whole numbers to investigate their structure can support a flexible approach to problem solving.
Second implication.
Considering the multiplicative structure of numbers can highlight generalisations about their properties.
Paragraph 2.
Odd and even numbers are often some of children's first experiences of seeing the multiplicative structure of numbers. It is suggested that activities in which students physically sort groups of objects into regular arrays of width 2 can support a recognition of the way even numbers can form a rectangle and odd numbers can form an L shape, and this supports pattern spotting and generalisation.
Reference 8.
Providing the opportunity to explore which numbers are made of pairs, can be split into 2 equal groups, and can be split into equal groups of 2, is more helpful than a reliance on identifying the last digit of a number as a characterisation of the 2 times table.
Reference 9.
Students do not necessarily connect doubling with multiplying by 2.
Reference 10.
Or recognise that when operating on whole numbers, doubling will always produce an even number, and so need support to do so.
Reference 11. There are 4 implications of paragraph 2. First implication.
Activities in which students sort objects into 2s can helpfully lead to the visualisation and then generalisation that even numbers can form a rectangle and odd numbers an L shape.
Second implication.
Exploring which numbers can be split into 2 equal groups and also into equal groups of 2 supports conceptual understanding that even numbers are divisible by 2.
Third implication.
Learning a list of digit endings as a way of identifying odd and even numbers does not support conceptual understanding of whether or not the number has a factor of 2.
Fourth implication.
Doubling needs to be explicitly linked to multiplying for students to appreciate when it will always result in an even number.
Paragraph 3.
A variety of representations and contexts are suggested for exploring multiples, numbers that divide exactly by another without a remainder, with the goal being for students to identify patterns and be able to generalise characteristics.
Reference 12.
Conceptual understanding of divisibility should be established before introducing divisibility rules and procedures.
Reference 6.
Vocabulary needs careful attention as reasoning with and about multiplicative number sentences can lead to words such as multiple, an object, and multiply, a process, being mistakenly used interchangeably.
Reference 5.
Development of multiplicative reasoning can be blocked if multiples are visualised via repeated addition rather than scaling or growing, and this creates difficulties in coming to understand a number's structure as a product of its prime factors.
Reference 13. There are 4 implications of paragraph 3. First implication.
Using a range of representations and contexts when exploring multiples supports students' pattern spotting and generalising.
Second implication.
Conceptual understanding of divisibility should be established before rules or procedures are introduced.
Third implication.
Careful consideration of the specific vocabulary being used, such as odd, even, factor and multiple, is recommended.
Fourth implication.
Visualising composing numbers multiplicatively by scaling or growing rather than additively helps support multiplicative reasoning and generalising.
Paragraph 4.
A tendency to define primes by what they are not
Reference 7.
can result in misconceptions that prime numbers are small, under 100, and that every large number, if composite, that is, having more than 2 factors, is divisible by a small prime number. Students have a tendency to calculate the product of prime factors and then divide the answer to check for divisibility, rather than reasoning flexibly.
Reference 6. There are 2 implications of paragraph 4. First implication.
Working with characteristics of primes, rather than what they are not, can help avoid misconceptions about their size and prevalence as factors of other numbers.
Second implication.
Practicing seeing prime factors both individually and in combinations can help support flexible reasoning about the divisibility of the entire number.
Paragraph 5.
There are 3 common approaches to finding the lowest common multiple. A. Set intersection, finding a number that appears in a list of multiples for each. B. Creating a multiple and then dividing, checking for divisibility by the second number through an ordered list of multiples of the first. And C. Prime factorisation, finding the minimal product of prime powers that contain both their factorisations. However, students often seem unable to recognise the equivalence of these methods.
Reference 13.
A useful suggested approach to finding the highest common factor of 2 numbers is using a Venn diagram representation, where each circle or set contains the prime factors of its respective number, with any shared prime factors placed in the overlap. These shared prime factors can then be multiplied to find the highest common factor.
Reference 4. There are 2 implications of paragraph 5. First implication.
Making links between different methods of finding the lowest common multiple of 2 numbers can support conceptual understanding relating to factors and multiples, and also flexible problem solving.
Second implication.
A Venn diagram can be used to visualise common prime factors of 2 numbers, which can then be multiplied together to find the highest common factor.
The ESPRESSO also has an infographic titled Recognizing 24.
There are many ways to see a number, and it is useful for both teachers and students to visualise or think about numbers in terms of their properties. This infographic incorporates different ways of seeing a number, in this case 24. When you think about the number 24, what springs to mind? Can you imagine it as an array, a neat set of groups? How many groups are there? And how big is each group? Can you imagine it first as 2, doubled, then doubled again, and then multiplied by 3? What could this look like? For us, it could be a kind of 3-armed windmill. You might like to think about how you could fold and unfold a piece of paper to reveal each of your steps as a multiplication or division. What about imagining 24 as a flat square window pane that grows in all directions, first by a factor of 2, then 2 again, and then 3? Can you imagine each stage of this growing as a stack of flat window panes, each one larger than the last? How about imagining 24 as a tree or plant and breaking it down into its factors as each root branches downwards into the soil? The numbers at the ends of the first branching are 2 multiplied by 12, then further breaking down the 12 root into 2 multiplied by 6, then breaking down the 6 root into 2 multiplied by 3, so that at the 4 final ends of the roots are the factors 2, 2, 2, and 3. What about imagining a series of towers stacked up that all have a height of 24? What might the stacks look like? Can you see a tower with 24 blocks all the same size? Is there another tower of the same height, but this time made from only 12 identical blocks? What other block sizes might make a tower of equal height to these two? Thanks for sampling this new product. We loved you joining us. The details of the references are coming next, so feel free to listen or stop here, whichever you prefer. If you enjoyed this CoffeePod, there are others available and more recordings in progress. We'd love to hear your thoughts about this CoffeePod. Please email us at admin@cambridgemaths.org. And you can also read the original Espresso by going to www.cambridgemaths.org.
The Espresso has a reference list of 13 entries written using APA 7 notation. The references can either be accessed as a separate document or in the published Espresso via links in the video information box. Alternatively, you can continue to listen to them here. Reference 1. Templeton, G. 2020, April 29. Why should we care about prime numbers? Mashable.com. Reference 2. Mazer, J. 2014, Enlightening Symbols, A Short History of Mathematical Notation and Its Hidden Powers. Princeton University Press. Reference 3. Mason, J., Stevens, M., and Watson, A., 2009. Appreciating Mathematical Structure for All. Mathematics Education Research Journal, Volume 21, Issue 2, pages 10 to 32. Reference 4. Kurtz, T.L., and Garcia, J. 2012. The Complexities of Teaching Prime Decomposition and Multiplicative Structure with Tools to Pre-Service Elementary Teachers. Journal of Research in Education, Volume 22, Issue 2, pages 169 to 192. Reference 5. Zazkis, R. 2000. Factors, Divisors, and Multiples. Exploring the Web of Students' Connections. In E. Dubinsky, A. H. Schoenfeld, and J. Caput, editors. Research in Collegiate Mathematics Education, Volume 4, pages 210 to 238. American Mathematical Society. Reference 6. Zazkis, R. and Campbell, S. 1996. Prime Decomposition, Understanding Uniqueness. The Journal of Mathematical Behaviour, Volume 15, Issue 2, pages 207 to 218. Reference 7. Zazkis, R. and Liljedahl, P. 2004. Understanding Primes, The Role of Representation. Journal for Research in Mathematics Education, Volume 35, Issue 3, pages 164 to 186. Reference 8. Griffiths, R., Gifford, S., and Back, J. 2016. Making Numbers, Using Manipulatives to Teach Arithmetic. Oxford University Press. Reference 9. Zazkis, R. 1998. Odds and Ends of Odds and Evens, and Inquiry into Students' Understanding of Even and Odd Numbers. Educational Studies in Mathematics, Volume 36, Issue 1, pages 73 to 89. Reference 10. Harrell, G., and Comfrey, J., Editors, 1994. The Development of Multiplicative Reasoning in the Learning of Mathematics. SUNY Press. Reference 11. Ryan, J., and Williams, J., 2007. Children's Mathematics 4 to 15, Learning from Errors and Misconceptions. McGraw-Hill Education, UK. Reference 12. Vanden Heuvel-Panhuisen, M., Editor, 2008. Children Learn Mathematics, A Learning Teaching Trajectory with Intermediate Attainment Targets for Calculation with Whole Numbers in Primary School. Sense Publishers. Reference 13. Brown, A., Thomas, K., and Tolias, G., 2002. Conceptions of Divisibility, Success and Understanding. In S. R. Campbell and R. Zazkis, Editors, Learning and Teaching Number Theory, Research in Cognition and Instruction, Volume 2, pages 41 to 82, Ablex Publishing.